Okay, hi everyone. Well, this is a somewhat different live stream than our usual because I'm at a conference, well, at least virtually. Conference is Programming Research in Mainstream Languages. And I said that I would talk about designing a full-scale computational language, 40 years of language innovation. So I thought I would talk a little bit about some things that we've learned about programming, sort of the process of programming, the theory of programming, the practice of creating languages and so on over that period of time. And I'll probably touch on a variety of different kinds of sort of core issues of programming. And I invite people both locally at this conference and out there on the live stream to ask questions and so on. So maybe I should start off with kind of an outline of how we got to where we are right now. So the language, our Wolfram language system, we started building it in 1986. The first version was released as Mathematica 1.0 in 1988. So that means we've got pretty close to a third of a century of experience with our language. And I'm very satisfied that a program that was written in version 1.0 in 1988 will still run today. So that's an unusual achievement among languages of any kind. But I should explain that, in a sense, our language, it's widely used as a very high-level programming language. But as far as I'm concerned, its aspiration is something bigger than that, what I call a computational language. And kind of what's the difference between these? We'll talk about that in more detail. But I see a programming language as something where there is a computer. It has certain operations. It can store data in memory. It can add registers together. It can do all these kinds of things. A programming language is something which is built to sort of tell the computer at that level what to do. And you build up a sort of a giant bureaucratic mechanism, in a sense, for how to create large programs, how to organize large programs, how to get large programs to work the way you want them to work. And then given that, you might build up libraries that do specific kinds of things, but the language itself is the small thing that is just dealing with sort of the core operation of the computer and getting and sort of managing the core operation of the computer. Computational languages, well, our computational language, the aspiration is something rather different. The aspiration is take things that exist in the world, whether they are algorithmic kinds of things with data structures and graphs and whatever else, or whether they are sort of more actual things in the world like cities and geography and chemical elements and chemical reactions and things like that, and represent all those kinds of things computationally. Have a language which, like human natural language, encompasses all those kinds of things that we think about in the world, and then provide a language that allows people to kind of systematically do computation with those kinds of things. And sort of one of the little footnote pieces to such a language is, oh, and by the way, it needs kind of computation level knowledge of sort of everything in the world. It needs to know about sort of all the cities that exist and all the chemical elements that exist and all these different kinds of things. So in addition to the purely sort of the traditional kind of computation side of things, you also need to know have a lot of knowledge about the world as it is. But the goal is to have, in a sense, a notation for representing the world computationally, and to be able to then specify things in terms of that sort of notation. And I kind of view what we're doing at a sort of larger level as kind of the update to something that happened about 400 years ago with mathematics, which was before 400 years ago, if you want to do mathematics, you did it by talking about it with natural language. Then about 400 years ago, people invented our mathematical notation, plus signs and equal signs and things like that. And that's what kind of launched the possibility of things like algebra and calculus and kind of the mathematical sciences. Kind of the way I see our mission in building our computational language is to enable the same kind of thing for kind of computational X, for all kind of enable the kind of computational fields, not just sciences, but make it possible to kind of think about things computationally and deal with the world computationally, so to speak. And that's relevant. A kind of thing that we're somewhat involved in is things like computational contracts for things like blockchains and other things, where the goal is to take what would be a piece of legalese, something written in English or some other natural language that represents a contract, and to be able to convert that into code that can talk about the real world enough to be able to say things in a computational way about the real world to put into that contract, for example. So, a little bit of kind of, let's see. I mean, a little bit of personal history that's perhaps relevant is I've kind of alternated between doing essentially basic science and technology. Most of the technology I've done is building computational language, but I've kind of done that alternation about 5 times in my life. And each time it turns out that the technology I've built is super useful for the science that I'm trying to create. And then, perhaps in a bigger surprise, the science, which is very basic science, turns out to inform the technology we can then build. And one thing I thought I would try and talk about today is actually a big surprise to me in recent times. So about 2 and a bit years ago, I kind of picked up again a project that I had launched ages ago of using kind of computational ideas that maybe I'll describe some of to find a truly fundamental theory of physics, to find something which is sort of underneath space and time and so on, and from which sort of the structure of physics can be built up. Well, the big surprise is that it's actually worked. And there's a sort of an increasing effort actually right now. We have our annual summer school, which we've been doing for many years, but we just added a physics track. So we have about 30 physicists right now working on all kinds of interesting projects, which I'm about to see the final results of in the next few days, actually, about things related to our physics project. But the basic point from a science point of view is it's really rather spectacular, because it really looks like we found sort of the machine code for the universe, on top of which a lot of existing very abstract areas of mathematical physics seem to fit very beautifully. It's kind of like a moment, a little bit like what happened in the early days of computation, when people had invented combinators and general recursive functions, lambda calculus, things like that. But it was a little hard to tell what these really were. And then Turing machines came along, and it became a little bit more concrete what was actually happening. I think what one sees with our models in physics is something a little bit like that. It's a little bit different level because we're sort of lower level than other kinds of models, but we see the same kind of way in which these other approaches, for example, from higher category theory and from, causal set theory and things related to string theory and loop quantum gravity and all these kinds of things, all turn out to sort of fit on top of, actually the last 2, we don't yet know for certain, but we're pretty sure how those work, sort of fit on top of the kind of machine code that we've created for physics. And the thing that I think is particularly relevant here is, okay, so we've got this model for physics. I'll describe it a little bit later, perhaps. It's like, what's this relevant to? Well, it turns out that the physics is just like a big example of distributed computing. The physical universe is basically doing a giant distributed computation. In fact, one of the things that for me was kind of a cognitive block in finding this theory of physics was the realization the universe is just an unbelievably profligate waster of computational effort. Just immense amounts of computation are happening to lead to the rather we only see a very tiny little piece of what's going on. But it turns out that the way the universe works is a giant distributed computation. It's maybe, in some general terms, it's like 10 to the 400 parallel threads going at a particular time in the actual behavior of the universe. But that's a rough estimate we have. I'm not sure that's right. We'll probably know. Hopefully we'll know from experiments within the next few years. But that's sort of a rough estimate. And the thing that's perhaps most interesting is that, so we have now this thing that the universe is doing a distributed computation, but actually we know quite a lot about how the universe works, because we know things like general relativity and quantum mechanics and so on. We know all this stuff from physics. And so the really interesting thing now is we get to take sort of the successes of physics over the last century or so and import them into distributed computing, and kind of try and reason about distributed computing using ideas from physics, using things like, and what we'll talk about maybe a little bit later, perhaps, is concepts like programming in a particular reference frame, and using that as a way to sort of unravel one's understanding of distributed computing. anyway, I'm getting a little bit ahead of myself. So I should probably start off and explain a little bit about kind of kind of how we see Wolfram language and how that works. And the thing I think I would like to emphasize is that in what has happened is we've gradually understood more about what computation is. And as we understand more about what computation is, we get to understand more about how we can set up a language that makes use of computation. We've kind of been building this tower, and the taller we build the tower, kind of the further we can see. And the thing that is really the big limitation, what is a programming language? What is a language? In a sense, there is out there in the sort of computational world, lots of things that computers could in principle do. Let me just show you. I mean, the thing that I've been very much interested in is kind of the question. One of the things, one of my sort of big scientific efforts starting in the 1980s was sort of using programs rather than equations as foundations for science. And so that gets one into the question of, so what, if one is using programs rather than equations, what programs might nature actually use? And so that gets one into kind of, well, what do simple programs typically do? And one might think, simple program, just do simple things. You might not think that if you do programming language research. You might think, although this is so. So here's an example of a very simple program. This is a cellular automaton, so it's just got a line of black and white cells, and at each step there's just a rule that says how to color the new cell based on the color of the cell above it and to its left and right. So if we look at that, then we can say, let's make one of these cellular automata. Let's use this one here. Let's just say started off from one black cell and run it for 30 steps or something. And and say make. I just said mesh. Just make. Okay, so that's just running that rule for 40 steps. Okay, so this is in a sense your very simple program. Here's what it does. Okay, let's try some other programs. Let's just make a table of all possible programs of this general type. Okay, so let's say we make we say this, and we say make a table of those. Let's say the first 64 of those programs. And this is what they do. And so what you see here is many of these simple programs just do simple things. Well, these ones are a little bit more ornate. They're making these nested patterns and so on. But this is my all-time favorite science discovery. This is Rule 30. You can see it starts off from just one black cell there. Let's look at what Rule 30 actually is. It's just this. You can think about it if you really wanted to. You can think about it as a Boolean function. This is, let's see, we can just write down its Boolean function. This is 33. Okay, there we go. All right, let's do, let's say Boolean minimize. Let's make, I think its default is DNF. So we can say, convert that to a DNF. Okay, that's a pure function. So we can say ABC here. Okay, so that's what this thing is as a Boolean function. Okay, so it's a very harmless thing, the kind of thing somebody just might put into a program anywhere. Okay, what does it actually do? Well, let's run it for 30 steps. This is what it does. Let's run the corresponding thing for, let's run it for 400 steps. Let's say this is what it does.
Stephen,
yes.
What is a DNF?
Say that again.
What is a DNF?
What is disjunctive normal form?
That DNF. Okay, sure.
I figure based on what you have on your whiteboard, I know you know what that DNF is. I thought I would just show this as an example. So okay, so this is a it's just running that Boolean function over and over again. And this is what it does. Okay, so this is really a very surprising thing. It's like very simple function, run over and over again. Somebody's saying increase the zoom level. Let's go ahead and do that. Run that function over and over again. Here's what you get. So one lesson for this is well, let's say, this is kind of an example of what programs in the wild do. And so, for example, when you think about debugging programs, let me give you an example. Let's say we have this program. This is a different example of the same type of rules as Rule 110. You might say, okay, I want to prove the theorem that this trail here will never die out, let's say, okay? How do you prove that? Well, you can run, let's say you run for 1,000 steps, it's still flapping around. You run for, I don't know, 3,000 steps. And okay, after 3,000 steps, you can kind of see that it's done something, it's evolved to something fairly simple. So one feature here is that this rule, you can say, how do we characterize what kind of computation this is doing? How do we characterize what's involved in the proof? One of the things that's come out of my study of sort of simple programs in the computational universe is this thing I call the principle of computational equivalence, which basically says that most simple programs whose behavior is not obviously trivial turn out to be equivalent in the sophistication of computations they do, or in particular turn out to be capable of universal computation. And so in this particular case, let's say instead of just starting it off from a single black cell here, we just start this off from a random initial condition, let's say, I don't know, 2,000 across random initial condition. Okay, if I do that, you can see that the thing generates, just the simple cellular automaton is running, but you can see it's generating all these little structures. And you can kind of imagine that maybe those structures could represent kind of logic operations, and that somehow some combination of those structures would let you do an arbitrary computation. And indeed, that's true. Indeed, it is true that Rule 110 is capable of universal computation. So even though the rule was just this very trivial, you might have just picked it at random type rule, the behavior is sort of as computationally sophisticated as anything, and for example, is capable of universal computation. So that means, for example, that this question, that there's this phenomenon that I call computational irreducibility that has to do with how do you know what's going to happen in one of these systems? So for example, you're running a Rule 110 or Rule 30 or something, you say, what's going to happen after 1 billion steps? So one way you can tell that is you run the 1 billion steps, you see what happens. Another thing you can try to do is to say, let's prove a theorem, let's make a formula that kind of jumps ahead and works out what's going to happen after 1 billion steps, but just by using a little piece of math or something. So this phenomenon of computational irreducibility, which basically follows from the principle of computational equivalence, says that you often will not be able to do that. In other words, to know, for example, what's eventually going to happen, what's going to happen after 1 billion steps in Rule 30, you pretty much just have to follow 1 billion steps and see what happens. So if you want to know a question like, will Rule 110 ever do such and such, that will be undecidable. So what's interesting is that in, for example, so cellular automata and a lot of other kinds of simple programs that I've made up have gotten very widely used as actual models of natural systems. So they're used for simulating all kinds of things. And if you ask in those simulations, if you say, can I prove that in this simulation of such and such a thing, such and such will never happen, that will be something where there's computational irreducibility and where that proof can be in general undecidable. So it's a case where if the things that you're doing, if the programs that you're writing are programs that correspond, let's say, to something like this, then the kind of the hope that you can sort of make a safety net and say we can prove nothing bad will ever happen, it's just not possible. And the question is then, so one of the questions, which is sort of an interesting question of both mathematics and computation, is, to what extent can one hold undecidability at bay? I mean, it's important. And so here's the trade-off. If you say, I want a system where everything is decidable, where there's none of this stuff where it can just go off and do this irreducible computation and you can't know what's going to happen. In that model, in that setup, you are constraining, you're deeply constraining the kind of computation that your system can do. If you want the system to take advantage of everything computational that's possible, everything your computer can in principle do, you need computational irreducibility. If you have computational irreducibility, then you have undecidability and you have all these kinds of issues. So it's kind of a trade-off. Do you want a system where you've boxed in what it can do, or do you want your computer to kind of have its head and be able to do what, be able to sort of operate to its maximum extent in which case you inevitably have computational irreducibility, and there are inevitably things where you can't kind of constrain what it does. And that's relevant, I don't know, in areas like computer security, that's highly relevant. In fact, this principle of computational equivalence is important in computer security because, you build a thing and it's supposed to be, operating a doorbell or something, and you think it has a simple kind of computational setup, but actually somewhere in there is something like a Rule 110 cellular automaton that you can program, and people have managed to embed Rule 110 in an amazing range of different kinds of things, and including all sorts of spreadsheets and blockchain protocols and all kinds of things like this. And once you have that, you're capable of universal computation. And once you have that, you can kind of then sneak around and program your thing to do sort of anything. And even though you thought, oh, I've got this very constrained system where I can know that it won't do anything bad, you can end up with a situation where you can get further. So this is kind of one of the big learnings from science that I've done, is this kind of point that even when programs are simple, their behavior can be sort of arbitrarily complex. And arbitrarily complex in the sense that they sort of reach the maximum level of computational sophistication. And so that's an important principle in science. I'll talk about later how it relates to fundamental theory of physics. But that's an important principle in science. It's also an important thing to think about when you think about programming and languages and so on, because what is a language supposed to do? Well, on the one side, we have what a computer is computationally capable of. It can run all these kinds of things that do all these very complicated things. That's what a computer can do. Then on the other side, we have us humans thinking, what do we want to do? What do we want to compute today with our computer? And so a language, as far as I'm concerned, is the bridge between the things that a computer can compute and the things that we care about computing. So a language effectively has to represent, has to take our thinking and represent it in computational form so that we can communicate it to a computer to get it to do what it can computationally do. Now, one of the challenges is some of what you can computationally do here is something that is not really things of interest, currently of interest to humans. There's kind of an issue here of kind of what thing do we actually want? Let me just save this notebook here for 1 second. That's odd. Okay. So one of the challenges in creating a language is, what do humans care about computing? And of the things that sort of naturally get computed, what can we even understand right now? So one of the things that I've noticed over the 40 years that I've been building languages is there's a steady increase in what humans sort of have enough ambient knowledge to be able to deal with, particularly in areas like functional programming. When I first introduced functional programming constructs in SMP, which was the forerunner of Mathematica and Wolfram language, back in like 1979, people were like very confused. And gradually over the years, we've been able to make more and more use of those kinds of things because people can understand them and people care about the operations that they do. And maybe just sort of segueing into a slightly different direction. I mean, if you're interested in, well, let's say machine learning kinds of things, let's do some simple piece of machine learning. I don't know. I can say something like, well, let's do. Now I'm sort of jumping ahead a lot, but in our language, what happened here? In our language, let's say, I don't know. Let's get picture of an elephant, for example. And so here I'm using, this is sort of an interesting feature of the language, I'm using natural language as the input method to create something which is ultimately a piece of symbolic language, African bush elephant, species specification, an image property of that, and then I get a picture of an elephant. And now I could, for example, say something like, let's do this, let's say net model, let's see, what do I want here? I want, there we go. this neural net, and I'm going to put the picture of the elephant in there. Let's see what happens here. We might have to load in this neural net, and then this is going to probably identify, who knows what it will identify this thing as. It might take it a moment here to load in this neural net. I don't know why it's taking quite so long here. Something odd is happening. There we go. I don't know why it. Okay, so it's downloading a 65 megabyte thing. Okay, great. It said it was an African bush elephant. Terrific. Okay, let's say I look inside that neural net. I mean, if I just looked at that neural net, let's say let's say I just say take the first 5 layers of the neural net and only apply the first 5 layers of the neural net to my elephant. Okay, that wasn't so helpful. Let's make those, so I'm mapping image over these. So that's then showing the inner thoughts of the neural net, pondering its identification of the elephant. And so this is a case where we don't have a good language for describing what the neural net thinks inside. This is a place where we haven't managed to get to the point where we can connect kind of the sort of human thinking about things with the language that is relevant for describing what's going on. Another example, let me show you one other example. Let me show you, let's try this. So let's try, okay, so there is an axiom system. Let's see. Here we go. So this is an axiom system that I found 21 years ago. It's actually the simplest axiom system for Boolean algebra. So now we can say, let's take that axiom system and let's say, can we prove the theorem that, let's say P, I think it's, we're using center dot here. No, we're using, what are we using here? What are we using as the operator there? We're using that kind of dot. So let's just paste that in, equals Q and that kind of dot, P. So we're trying to prove commutativity using this axiom here. So let's see what this does. So this is now doing equational theorem proving, and it will hopefully generate a proof object. There we go. Okay, so it's a 102-step proof of that result. And if I say something like, show me the proof data set, this will now show me the steps in that proof. These are equational steps in the proof. If I wanted to, I could take line 20 and I could say, just show me the proof, I think it's proof graph. So this is now a graph that represents each, these are different kinds of lemmas. Those things are critical pair lemmas, those are substitution lemmas. This is proving that original proposition, proving it using that axiomatic system that I've defined. But now one of the things that's interesting again about this, the steps in this are basically incomprehensible. We don't have a way of describing these things that is sort of that bridges to what we humans understand. Yes, we can compute this, but we don't have kind of a language to describe what's going on. In fact, one of the frontiers of some of the language development, so pure language development that we're doing is essentially languages for proofs, being able to take what we know from representing computation and also use it for representing proofs and sort of making human understandable proofs. This is a proof that we know is correct, but it's not something that we as humans can kind of take a piece of and find useful. Okay, so let's just in terms of the language in general, the sort of the idea of Wolfram language is just that you are able to represent, I don't know, whatever kind of thing. Maybe it's an abstract thing like a graph. You can then say, just take that graph and make a plot from that, make some kind of community plot from that graph, or you can deal with images, you can deal with all kinds of other sorts of things. A very important feature of the language is it's a symbolic language. So X is just X. And if I just say something like, X to the 10th minus 10, just X to the 10th minus 10, I could say factor that, and it will be then treated as a symbolic thing that is then going to have symbolic operations done on it. Well, one of the things that we've learned over the years is all the things that can be represented symbolically. all the different kinds of things in the world. Like, for example, this notebook that I'm using is just a symbolic expression. We invented these notebook things back in 1987. They finally got copied by other people. It took a remarkably long time. This is, so we're, but everything that's here is just a symbolic expression. Everything, when I make, I don't know, what's a good example here? Well, if I mean, rather trivially, if I have a piece of, well, let's say I have a 3D graphic of a dodecahedron or something, all of this is just symbolic expressions. That's just a symbolic expression that represents a dodecahedron, and we can do things with it. We could say, what's the, I wonder whether this will work. What's the area of the, that's, I guess, what do we want to say? We want to say surface area of a dodecahedron. There we go. So that's the surface area of the unit dodecahedron. And again, all these things are just symbolic objects. So what else can be a symbolic object? I don't know. The where are you guys? You guys are in Edding. Some of you, I don't know where. I spelled that wrong, but it's spell corrected anyway. So, that's a city. That's just a symbolic object. What really is it to the language? It's just an entity of type city, and it's Edinburgh, UK. Okay, so what? Well, we can take that entity and we could say something like, we can now use knowledge of the world. And so we can say, what's the population of Edinburgh? Or we could say something like, let's do the following. Let's say, let's do this. Let's say geo-nearest of, let's say, volcano, to Edinburgh. Let's say the 10 closest volcanoes to Edinburgh. And let's see, we can say, and these are, again, just entities. They're just symbolic entities that we can manipulate. So we could say something like, make a geolist plot of these. And so this will probably show us the locations of those volcanoes. Or we could say something like find shortest tour. We could just do, and let's see, that was on line 34. We could say find shortest tour. So that's giving us a 1500. I wonder why it's in nautical miles. I think this has probably been set up for some, this machine has been set up for some different purpose. But anyway, this is just telling us an ordering of those volcanoes that will give us the shortest tour. We could probably plot that tour if we wanted to. But so what we're seeing here is these are just symbolic entities that we can compute with. And we can do all kinds of computations with them. I mean, here I did a shortest tour. I could do all sorts of, I don't know, let's say, let's do this. Let's say, geograph plot. What could I do? Let's say I just take that line 34 and I say nearest neighbor graph. So I say of line 34 with everything getting its 3 nearest neighbors. That's interesting. Okay, so I need to say here the distance function is geodistance. Let's see if that works. So this is now taking, this is now computing nearest neighbors by using geodistance on those particular things. I don't know why it's taking it quite so long. I probably should think about what it's doing. But anyway, strange. All right. Well, but in any case, the thing, the thing that's important here is we get to sort of mix this by virtue of this kind of symbolic representation of things. We get to mix things that are doing graph theory, things that are doing combinatorial optimization with things that are doing geography and so on. And that's a very critical feature of our language, and something where as we've kind of understood more about what programming and doing things with languages corresponds to, we make use of these facts. So for example, lots of things are symbolic expressions. So for example, processes, let's say I can say launch kernels. Let's see what happens here. Okay, so this is launching some parallel kernels. It's actually only, what is it doing? Oh my gosh, this is probably going to launch all the kernels on my local network. Okay, it was probably set to do that. So this is now going to set something up to do parallel computation. But what you'll see is that the individual kernels that are running on different cores on my little local network are all represented as symbolic expressions. We'll probably see this come back as a great big long list of, I don't know why this machine is running so slowly. Okay, as a great big, oh, there we go. So those kernel objects are just symbolically represented kernels, and we could say something like remotely execute something on that particular kernel, again represented as a symbolic expression. Or we could say, if we wanted to, we could just say parallel table of something like dollar process ID. That will be the process ID for the process that the kernel is running. Let's just make 400 of those. Then we'll get that will be running across all those different parallel computers. And so if we say, counts of that, it will show us how many processes effectively were allocated, how many computations were allocated to each processor there. Okay, so in any case, the main point here is symbolic language, able to represent lots of kinds of things, able to have us ask questions about all sorts of computations. So for example, let's say we have a function like nest list. We could say nest list fx10. Okay, that's what that would look like. That's just nesting that function. Maybe the function is framed. We can nest like that. Or maybe the function, let's try this. Let's say nest list blur. And let's say something like, let's start off here, picture of Eiffel Tower or something, and that will now use natural language to compute a picture of the Eiffel Tower, and let's blur that 10 times, and then again, these came out rather small, but we can see, the result of successively blurring our Eiffel Tower. And again, this is now a simple programming construct. But now that we have sort of the idea of functional programming and symbolic computation, we can start inventing things like not just nest list, but nest graph. So for example, we might say, I should explain, this is a notation for, okay, here, let me write this out in more beautiful form. Let's say x is the function, f of x, g of x. So that's a lambda or a pure function, whatever you want to call it, started off from, let's say, 0, and run this nest graph 4 times. And let's, okay, so that will make a graph. Actually, if I wanted to, I could say here, vertex labels, arrow automatic. And now I'll see, it's kind of wrote over itself here, but you'll see this is doing the nested graph operation here of, it's creating this nest graph. And it turns out nest graph is a very useful general operation, but it's something where until you kind of understood, until you had graphs as sort of first-class things in the language, it's not this is something you kind of have the idea of doing once you have these other kinds of constructs in the language. So for example, let's say we do something like, let's try and take an example. Let me try and, let's do something like, here, I actually had an example here. Let's say we have this nest graph idea. So we could say, let's take countries that border Switzerland and let's sort of make a graph, let's say vertex labels to automatic, just so we can see it. And so now this is then computing the nest graph of sort of the bordering relations between Switzerland and countries that border it and so on. So once we have this kind of idea, nest graph is an example of a programming construct that sort of starts making sense in this kind of symbolic context and so on. Now, I should explain kind of what is the foundational idea of our language. It's a symbolic language, and the absolutely foundational thing that it does is it transforms symbolic expressions. So for example, how do you define a function in our language? So let's say we have a function, let's say we're defining a Fibonacci. How would we do it? We would say, f of 1 is equal to, let's say, f of 2 is equal to 1. Okay, great. So that says that defines the symbolic transformation that f fib of 2 is 1. If I say what's fib of 3, it'll just say I don't know what fib of 3 is. Okay, so then we can define a transformation rule that says fib of blank, fib of blank is, and that we're naming that blank n, is, let's say, fib of n minus 1 plus fib of n minus 2. And then we can, say what's fib of 10 and so on, and we'll get these results. We could also have done this completely symbolically. In fact, if this particular symbolic computation, it will, if I just run this, it will blow up, because it's just going to say fib of n minus 1, n minus 1, n minus 1. One of the things that's actually an interesting current challenge, which I can talk about a little bit more, is the representation of that execution history, and in particular, the kind of way in which that evaluation of execution is done. And one of the things, it's kind of a spoiler alert, it turns out that question of the order of evaluation of all the different Fibonacci's in there is essentially the same question as the selection of reference frames in relativity and in general relativity in the theory of gravitation. It may seem like, how could these things possibly be related? And it's sort of funny, because I was thinking about these things back in around 1980, and I was both thinking about how to create a language that was based on transformation rules for symbolic expressions in which these questions about evaluation came up. And I was also thinking about gauge field theories, where all these questions about gauge choices and reference frames and so on come up. And I had no idea that these were connected. In fact, until, 30 years ago, I kind of got some idea they were connected. And then about a year and a half ago, I really realized these are essentially the same problem. And so that's kind of a thing to comment on. Now, one of the things I might mention, this process. Go ahead.
Sorry, Stephen. So I was told that you'd like to see the reaction from the audience and connect to that. So I'm going to ask you. So we, a lot of us know that your language is very impressive with what it does, and you have managed to impress us quite a number of times in this talk. But as a programming languages person, I am in particular more interested in seeing, what's going on behind the scenes. How is your language? So do you, for example, have a formal specification of your language now that you have like theorem provers and all that? Do you have what do your language people do? I know that you broadcast your CEOing of the language every week. And maybe you'd like to tell us a bit about the overall process and what you put in there and things of the like.
Yeah, okay. So, one question is, what should be in the language? In a sense, what should be in the language is those lumps of computational work that people repeatedly want to use. Those are essentially the functions in the language. Just like in human language, the words we choose to invent in human language are words that describe things we care about. In one of the big challenges in building Wolfram language is there are now 6,000 things that are words in our language, in effect. Sort of maintaining consistency and design coherence of all of that. That's one of my main activities. And that process of language design, it's something I think people don't think about too much, but it's something that for us, particularly as we build up a computational language rather than a programming language, where we actually have 6,000 primitive things in the language, so to speak, that's something that's sort of critically important. And so this process of things like, how do you figure out the name for some, I don't know, let's look at the core language here. Let's say list manipulation, that would be a good example. How do you pick out sort of the names for things that are going to be the primitives of the language? And one of the principles is, some things it's very easy to write some kind of idiom for some particular kind of thing if that idiom, if there is a good name that describes that whole lump of computation, then give it a name and make it be a function in the language. Because when people read the code from the language, that name helps them understand what's going on. If the name is utterly obscure, then it's better to have the idiom, because that way people can sort of read the idiom and understand what's happening, rather than kind of having to know some name that that they're not going to remember. So we're in a sense leveraging English as leveraging the fact that people know stuff about what words in English mean. But this is a big challenge to kind of figure out how should you name these lumps of computational work? What should those lumps of computational work be? Then in terms of the actual process, I spend, a bunch of my time actually doing kind of the design of the language. And let's see if I can pull up. I mean, as a piece of kind of, what can we call it? Reality computation or something. I live stream many of our internal design reviews. And so this is, of course, that's using our built-in video capabilities to go find all these thumbnails and things. But this is we've now got 474 episodes of kind of live CEOing. And all of these things are about the design of pieces of the language. Like this one is something you might have thought was kind of trivial, about a function called date setter and time setter. That what we do in terms of, we have a large team that's working on the development of our language. Kind of the way that we sort of control what's happening in some sense is, in the end, I'm the ultimate sort of architect to the functional design of the language, though what tends to happen is many people come up with proposed functional designs, and then I'm sort of the ultimate editor of that, of what's done. And for me, it's both very interesting and very challenging, because every area that we work on, whether it's computational geometry, whether it's lots of different kinds of things, what's needed for me is to really understand that area, to be able to make sort of what are the ultimate primitives from which we can build up the lumps of computation that are important for the language. So for us, kind of, we tend to be a write the documentation first type thing, more or less, of all these functions in the language. In terms of kind of the low-level specification, the core symbolic language, yes, obviously we have sort of formal specifications of how that works. In the kind of what is the formal specification of what a city is, well, that's a more complicated thing, because we're dealing with the real world. Some of what we have to deal with is things where the notion of a formal specification kind of degenerates, because it's like, okay, a city is a city according to the national census bureaus of the various countries. What's a country, et cetera, et cetera, et cetera. So there's kind of a gradation from things where it is just computational and where it's possible to give a very formal specification of what happens, and the kind of thing where which is more about sort of the real world and more about curating data from the real world and having processes for doing that and so on. Now, in terms of how the language is built, I don't know how big it is now, maybe 50 million lines of code. Most of them are Wolfram language code at this point. The original kernel of the language is in basically an extension of C that we developed back in the mid-1980s. I guess increasingly also in C++, but I think we're still using the extension of C that we developed that has all kinds of features that are useful to us. But in vastly more of it is written in the language itself. And for example, Wolfram Alpha, which is the stack that deals with, for example, natural language understanding and a bunch of our computational knowledge stuff. And it's the thing that powers sort of computational knowledge and things like Siri and Alexa. And it's also the thing that gets used as sort of the main API that gets called by computational contracts, smart contracts, and so on, that want to know something about the real world. Did it rain yesterday in Paris type thing? That's something you can ask that stack. So that's about, actually, I don't know in recent times, that's on the order of 15 million lines of Wolfram language code, I think, is Wolfram Alpha. So one of the things we've been doing, for example, in recent times, so we've always had various kinds of compilation for our language. One of the things that we're doing now is to build up a more sophisticated compiler for the language it's been a long-running process, and it's slowly producing more and more results. I'm not sure what I can show you that's all that exciting. I mean, I can show you basically, you know, I could just show you something that would be, you know, we can have one of these functions and we can say something is typed, and we could say it's, I don't know, whatever, an integer 128 or something, and we can make our function do the incredibly thrilling thing of saying, you know, add 6 to that integer. Okay, and then we can then, actually what I really should have done here, this is the wrong thing to do, but I should have done is tell it to generate LLVMIR, for example, from this. This is something which since we use this compiler primarily at this point for our internal code, the fact that there is a grotesquely long startup time here for the compiler is not so relevant. But here I can say, let's see, what do I want to do here? I want to show you I have to look up documentation to remember how to do this. Let's see, compiled code function. Okay, so I want to take, okay, well, I can say, for example, I mean, you know what LLVMIR code looks like, and I can, but you know, I could generate that from this. So a big thing that's important for this compiler is all kinds of automated type analysis, all kinds of automated unraveling of our symbolic language. And the thing that has been important to us is, yes, we have all kinds of sort of identities about the language that are encoded as symbolic transformation rules that say that this function is equivalent to this. There are properties of those functions that are known symbolically and so on. Actually, let me show you something else, which is also related to this. So this is one branch of kind of the use of the sort of meta-analysis of the language by the language. I'm not sure I can show you things that are sort of at top level visible that are so interesting here, but the thing that has been, I mean, an increasing fraction of our internal code, we're able to compile using this compiler, and there's a whole elaborate thing about how the sort of callback mechanism works into things that there's no point in compiling because they are lumps of computational work that are kind of already maximally efficient in the way that they're implemented in the language. But maybe I can show you another thing, which is another piece of, let's find a piece of code here. Well, let me see, I could write a piece of code. Let me write a random piece of code. So let's say I write, you know, let's do this. Let's say, let's be functional programming about it. Roman numeral /@ range of 100. Let's see. Okay, so that is actually I shouldn't have written out in this nice functional programming way. This is working out the string length of the Roman numerals of numbers from up to 100. Maybe I should write this out in a more mundane way. Let's see if I can do that. Of Roman numeral, let's just do a table here. Of Roman numeral of n, n goes up to 100. Okay, so that's going to do the same. Oops, that's going to do the same thing, at least if I got the code right. Okay, so one thing you see there, I mean, that's sort of a trivial thing is okay, so the question here, and this is a new experimental area that we're working on. And the question is, where is that actually? Is it in, there we go, analyze cells. Let's see what this does. So this is going to run code analysis on the cell, I hope. Oh, and it did nothing because there was nothing to analyze about the cell. All right, let me try doing something. Let me see. I have to make a mistake here. Otherwise it won't. Well, that's not very exciting. It's already turning it red because it knows that that doesn't fit. But what I wanted to show you, and I need a better example, is code analysis. This is again going to do nothing interesting. Is code analysis that actually going in and using essentially, well, rules, some machine learning, some theorem proving to guess whether the code that I just entered is actually correct code. So one feature of our language is, even this thing here, right? If I just enter this, it will, if I enter that, okay, it'll complain, but it'll still do something. I mean, if I got rid of that list line plot there, it'll rather boringly symbolically return all of those string lengths, okay? It'll complain, it'll say, oh, there's something went wrong here, but that's really mostly for humans at this point to see that. But if you ask the question, does it return a result? The answer is yes, it absolutely does return a result. That result is probably not what you want. But the question is, how do you define what you want? Because in a sense, the purpose of the language is to define what you want. And this was a piece of language that said what I wanted. It just didn't happen to be probably what I actually wanted. So that becomes a much more heuristic question. What, in our language, getting things that are just outright errors, it's hard to define what an error is. Okay, this thing is Roman numeral doesn't happen to be defined here with two arguments. If I wanted to, I could say unprotect Roman numeral, and I could say something like, unprotect Roman numeral, and then I could say, using our symbolic transformation ideas, I could just say Roman numeral of, let's say, n blank. Let's say that's, well, forget about whether it's an integer. N blank quotes hello is always equal to n squared or something. And now, actually, let me not put hello. Let me put anything in there. N blank of that is always n squared. And now if I do this, I'll get a bunch of, it'll still be asking for string lengths of numbers and so on. So the question then is this a reasonable piece of code, or is this likely to be wrong? And how can we help people understand that? And so there's sort of a big effort in this idea of code assistance. It's not yet a complete thing. I can maybe show you an example. There's just a post I wrote a month or so ago about version 12.3, and just all the new things in the 6 months before this came out. But let's go look at where we talk about code assistance. It's trees and things. Okay, that's videos, that's chemicals. All these things are just symbolic expressions that you can sort of do functional programming on, and that's what makes everything very powerful. That's generating Arduino code. Okay, here we go, code assistance. So maybe I wonder if I can pull up one of these examples. And okay, let's pull up this example here. Okay, so let's do this. And let's say, take this cell, and I hope I can say, analyze cells here. Let's see what that does. There we go. Okay, so this is now saying, rather uninterestingly, both branches of if are the same. Okay, so it's a very straightforward kind of thing. And then here we'll get some kind of set of choices about what we might want to do. But the goal here is for both novices and sophisticated programmers, be able to notice what kinds of things are wrong based on essentially, based on both theorems and heuristics about what a plausible piece of code is. So we ran this, the current version of Code Assistance on our internal code base of millions and millions of lines of code, and we found all kinds of nice bugs. It's sort of interesting to try and see in a symbolic language like this, what does it mean to do kind of code assistance of this type? I see there are a bunch of questions on chat, and let me try and address a few of those. And I thought maybe if people are interested, I could talk a little bit about the relationship of what we've discovered in our physics project and kind of my vision for the future of distributed computing. Let's see. David is asking, is there a computational language that uses formal sums and formal products of Feynman diagrams? Oh, that's a more interesting question than you might imagine. We are right now in the throes of understanding how these things we call multi-way graphs, which are essentially a representation of distributed computing, have correspondences to Feynman diagrams through kind of the intermediary of things like spin networks. Let's see. How similar is what we do to functional programming in Haskell? I mean, you'll find Haskell has different evaluation semantics and somewhat different objectives. I think you can almost run here. Here's a thing for if I do a greater than sign here, I can run various external languages. So I can run, and what's interesting here, I don't know most of these languages, but if I say, if I do something in Python here, I'll get back the result as a piece of Wolfram language code, and that's more non-trivial when you have more complicated data structures. I know we've been working on this for Haskell, and actually we need help from the Haskell community to make this external language connection work for Haskell. So if people here are interested in that, it's something that is sort of a coming attraction. I mean, there's all kinds of things you can do here. I know this is the shell. I wonder what on earth I will find out here if I say this. I'll get back. Okay, I'll just get back this object that is it's a symbolic object that represents the result of my shell command. Let's see. What does, somebody's asking here, what does symbolic mean? I mean, symbolic means that the thing can stand for itself. It means that the structure you build, in a sense, is just a structure that, as far as I'm concerned, what it means is that the structure you have is just a structure that you can pick up, and anything in the language, whether it's code, whether it's data of any kind, there's no distinction between those things. All of those things are just symbolic expressions that stand for themselves until they are evaluated, so to speak. And yeah, I mean, one of our goals, as I say, is to create a language. One of the points here, and this is one of the things that's been happening a lot, is people writing computational essays in which they're using, something where it's like, this might be a section on code assistance or something. People are using this notebooks and writing a mixture of text and computational language as a way of expressing themselves. And just like you can write well-written text that is a good way of expressing yourself, you can also write badly written text that's a bad way of expressing yourself. People are not as used to writing computational language that is a good way of expressing itself, so to speak. But that's something we're seeing, and it's coming more and more in our language, that people are using our language as a way to express themselves computationally and to sort of write good computational language that, together with sort of natural language, is the thing that is sort of the expression of their ideas. And that's, I think, an important idea that increasingly, you see that sort of things are worked out in computational notebooks and in computational essays, and then that all sort of gets ingested. There's all kinds of mechanisms for taking this and ingesting pieces of it into a whole source repository and doing all the kinds of things one needs to do there. I mean, I might say, people wonder about you were asking about behind the scenes things. We've obviously built up a big software quality assurance effort. That's all Wolfram language code, and it's all using essentially theorems about both our language and about the world. I mean, the price of a stock can't be negative. You might have thought the price of oil futures couldn't be negative, but actually you'd be wrong about that. And so it's a tricky thing, making theorems about the world when you're dealing with sort of validating things that aren't just pure sort of formal kinds of things. Let's see. Somebody's asking, Smek is asking, what is the most important sort of idea or concept necessary to create our language? I think the idea of symbolic computation, the idea that everything can be represented as a symbolic expression, the idea that that everything can be done in terms of transformations between symbolic expressions. Then the idea that everything in the world can be made computational. I would say those are the sort of three pieces of what's needed to, and then 40 years of work. And even the very concept that one can keep building more in that framework. Now, when I first started building all of this, I started building it kind of with my first language, SMP, Symbolic Manipulation Program, back in 1979. And at that time, my primary use case was mathematical computation, but I wanted to kind of drill down and find out what is the right kind of foundation for computation to use sort of underneath kind of the ideas of, underneath all of that sort of mathematical computation that I wanted to do. And that's when I kind of came up with this notion of transformation rules for symbolic expressions. Now, obviously, there was a long history in mathematical logic in thinking about transformation rules for symbolic expressions. And I have been very interested in that history. I think that in a sense, I'm sort of glad I didn't know more about that history back in the day, because I think some of it would have confused me. I mean, one of the things, as you may know, December 7th of last year was the 100th anniversary of the invention of combinators, or at least the announcement of combinators. And so we did a big event associated with that. And I just might mention a few things just in terms of sort of languages and their structure. So combinators, as you might recall, are these two transformations. They're very easy to state in Wolfram language. They're just these symbolic transformations. And by the way, it's no coincidence that they're easy to state in Wolfram language, because I knew about combinators when I invented Wolfram language. And you know, I was trying to make something where you could do transformations like this. Now, combinators are, the other feature of combinators is they operate on symbolic expressions. That combinator expression is a symbolic expression. If you apply those reduction rules, well, you get this result. Now, combinators have this idea of no variables. Nothing is named, there are no variables. What this is providing is essentially the ultimate plumbing of, it's sort of a world without nouns. It's a, you know, imagine a language where there are no nouns. And all that happens is you're defining how data is flowing around, and you've got this thing that is defining how data is flowing around. You feed it a bunch of data, and it okay, we've got a question here, which is kind of a silly question, but I'll maybe address it. Let's see, shall I go on about combinators, or shall I answer why libraries aren't what we're making? I mean, yeah, the whole point is to create a coherent language. I mean, this is what I've been trying to explain, is to kind of create a coherent language. And this is the unique thing that we've been trying to do in building this computational language. It's like, yes, you can make a library that does image processing and another library that does graph theory and so on. Here's the problem with libraries. The problem with libraries is a lot of those libraries, a lot of what's in the library is infrastructure. And it's like you make this library for doing images for this thing. And a lot of it is, you know, reading in images, outputting images, things like this. And then at the end of it, you got this one wonderful function that does something useful with images. The thing that, you know, what one notices is that you know, a lot of the effort is in building up that infrastructure. What we've tried to do is to build sort of uniform infrastructure that covers sort of all these domains where computation is relevant, whether it's, you know, computational geometry or machine learning, or whatever else. And with great effort, have those domains really fit together, and have it be the case that sort of once you, so for example, in developing our compiler, you know, we need a bunch of graph theory algorithms. We need some combinatorial optimization algorithms. For us, the use of those algorithms is kind of free, and it immediately fits in with everything else that we're doing because those things are already in our language. You know, when you build libraries, you're building these prongs, and then you get into this whole situation where I've got this library that does this, how do I make it connect with that library that does that, and so on. It's a very different activity, and it's one, you know, I could zero out the last 40 years of my life by saying, oh, let's just get people to build libraries. It'll be good. You know, that's not what we've done. What we've tried to do is to put all the effort in to build this kind of coherent language that lets people construct things and go on constructing things. Now, if, you know, there are things which are beautiful to represent in something like Haskell, and the idea is to be able to make use of our language for the things that you want to make use of it and to interoperate with all these other languages. And the whole fact that we can represent things symbolically is very important for that interoperation. And eventually that will be true with Haskell too. That just hasn't been built yet, because actually it turns out to be more difficult to do that in Haskell than in lots of other languages. I think that the thing that well, I can let me go on talking a little bit about combinators, just because it's perhaps interesting to see this as a kind of understanding of sort of the foundations of programming, because this, in a sense, was the first foundation for actually the first foundation for universal computation. It also happens to be an incomprehensible one. In 100 years, most people would say, "Oh yeah, I know about combinators, but I don't understand them." And this is a combinator in action. Now, I think I might want to show you, just for fun, I can show you some sort of what do combinators in the wild actually do. And for example, actually what I was showing up there was sort of the minimal combinators for things like, what did I have here? I had minimal combinators for, there are the minimal combinators for the Boolean operations. Again, quite obscure, but this is sort of compiling that Boolean function into combinators. And one of the things that comes out of the science I've done is that there are more things you can imagine compiling into than you might expect. So for example, if molecular computing had happened before electronic computing, we might be compiling everything into combinators, because actually combinators are not a bad meta model for kind of computation happening through chemical reactions and so on. So the I think let's see. So just about combinators, it's kind of fun to see. Somebody was mentioning busy beaver problems of, when you have a program, how long does it run? Let me show you an example. I think I have it here. Here we go. Here's a combinator. I could put it into my session here. Well, actually, let me just show you the results here. Well, actually, all of these things. Hold on. This is. Let's try this one here. Let's just paste this in. This is loading in a bunch of code that was used for that particular. Oh boy, this is making it with all the nice. We can forget all of that stuff. That was just making it for my particular thing for my post. Okay, so this is showing the size of the combinator expression that we get by evolving this combinator using those replacement rules. Okay, so that was for 1,000 steps. Let's run it for 10,000 steps. Okay, oh wow. Okay, so that thing makes a 50,000 intermediate combinator expression. It's still running. We haven't terminated yet. It's like if you're doing programming, if you're trying to prove theorems about programs, this is a bad one, because you're at 10,000 steps. It hasn't terminated. What's it going to do? Well, let me show you what it does. This is what it does after, let's see, 100,000 steps. Okay, after 36,536 steps, et cetera, et cetera, et cetera. This is what it does. It finally terminates. Okay, so this is undecidability kind of reaching its hand out, and in the case of these combinators. So one thing about these combinators is you think about the evaluation of that combinator expression, and each thing, there's a transformation rule that says S, K of X and Y goes to X, et cetera, et cetera, et cetera. S of X and Y and Z goes to blah blah blah. Those are evaluation rules for the combinator expression. So one big question is, in what order do you apply those evaluation rules? And so combinator expressions are trees, of course. So, if I say something like tree expression here, I can, I don't mean tree expression, I mean expression tree. Then I can see what that's like. Oh, that's very boring. That's because I need to tell it to, because everything is packed inside the heads here. I think if I say heads to true, is that going to do the right thing here? Yeah, okay, let's see whether this works. I think that's what I want. Well, I'm the reason I'm. I know. I see what happened. Okay, there we go. There's the combinatorial expression. That thing can be thought of as a tree. I mean, that symbolic expression in our language is a tree. It happened to have some things packed into its head. That's a rather interesting programming language story of when do you pack things into the head, so to speak. So, for example, when I defined a pure function, let's say I define the function x squared, apply that to y plus 1 or something, I'll get this. That is kind of a big head for the y plus 1 thing. And there's sort of a question of what kind of things can you put in. So this is kind of an adverb. This would be like reverse supplied of f. Apply that to x and y. That's reverse supplying f. So that's f of y comma x. And it's sort of interesting this is kind of an area where we're slowly experimenting with kind of adding more of these, what we sometimes internally call headdresses, these kind of adverb type operations. So somebody's asking, do you need to add type information to the functions you define? No, this is a language where the only type is a symbolic expression. So the way that you represent types of things is in a more flexible way than just saying there is a piece of meta information that is the type. It is more the structure of the object is representing the type of thing that it is. So, for example, if I make, I don't know, a graphics of a disk or something, you could say, well, what type is that? Oh, it's a piece of graphics. Well, but actually that you can deduce that from the head of this expression, that you can call that a type, but it is a much more flexible thing than a type. And one of the things we've learned over the years is that transformations for symbolic expressions are a great generalization of the idea of types. And of course, you can write a type calculus in terms of the structure of symbolic expressions, but it's a much richer kind of thing. So, for example, when it comes to sort of a low-level operation and getting close to the metal and compiling our language, yes, we're using we have a whole sort of way of understanding the types that are relevant to the bare metal of the computer. That is what's going on here. But at the level of using the language, you do not have to know about types. If you want to, there's actually a new thing we introduced for people who want to do sort of lower level things in the language. Is this, I wonder how to use this. Let's see whether we can do this. Not sure this is the right thing. No, this is a kind of a low-level representation of data structures, which you don't need in actually using the language. But if you're writing kind of low-level code, it's a convenient thing to use. And one of the things that's nice about it, which you might like, is that there is automatic visualization of all of these data structures. So you can create them in our language. And then, I don't know, let's say a linked list, for example. Let's do this. We're doing kind of very traditional sort of, but now this linked list is a symbolic data structure. And so, for example, we can go ahead and say, give us a visualization of that linked list. This is a good thing. This is a fairly new thing, which people seem to like very much for computer science courses and things. And it's something where, these data structures are low-level data structures, so they have guaranteed execution times and so on. At the level of something like solve this combinatorial optimization problem, the goal of our language is to do that as efficiently as possible using the sort of appropriate meta algorithms that we can, and sort of breaking down to lower level algorithms and so on. That's not something where we can say, oh, we can prove that the execution time is such and such. Let's say we're doing combinator reduction. We obviously can't prove what the execution time of combinator reduction is. But let me show you something else about combinators I think you might find interesting. And that has to do with, I mentioned that there are these different evaluation orders. And so what happens in combinators is, okay, here we go. So we've got a combinator expression, and we've got these rules that are to be applied to the combinator expression. The question is, which rule do we apply first? So what happens is we can have, for example, a leftmost, innermost evaluation strategy, where we say, crawl down the leftmost branch of the tree and do the innermost updates first. and we'll get some particular kind of updating scheme, we'll get some particular ordering for the combinator updates. And so now the question is, we can start asking so these are, for example, possible matches in the combinator expression that are possible things for the transformation rule. And so what we have to ask is we have some kind of ordering of these parts of the expression. How do we specify the ordering of those parts of the expression? We're now doing sort of a meta description of the evaluation process, and we need a language for the meta description of the evaluation process. And I will say, I have not figured out a good language for this. I built a language for this within SMP back in 1980 or so, and nobody, including me, probably ever understood that language. So this language is sort of the meta language for the description of the evaluation process, is something which is sort of a currently active area that I'm thinking about, and I actually have some ideas now which I think are going to be able to crack this. But the question that we can ask is, depending on what evaluation order we use, we might get different results. Like this is leftmost, outermost evaluation order. This is showing the size of the combinator expression. Eventually it terminates at this, I guess it terminates at this size. This is using leftmost, innermost evaluation order. It actually gets bigger. In the case of combinators, it is guaranteed to terminate in the same way. Combinators have this Church-Rosser property, this confluence property that causes them, whatever the evaluation order that's used, if they are going to terminate, they will always terminate in the same way. Now, one thing, of course, is that not all combinator expressions terminate. And so, for example, this is a combinator expression that with different evaluation orders, it will grow differently, but it will always grow infinitely. Okay, so now you might ask the question, is there a way of representing all possible evaluation orders? So yes, you can do that. This is what we call a multi-way graph. Multi-way graphs have been invented in a bunch of different fields with a bunch of different names. I called them multi-way graphs back in the early 1990s. That seems to be the least obscure name for them, because what's happening is this is a multi-way computation. So this is one possible reduction. This is another possible reduction. You could do the same thing with string updates if you wanted to. You could do the same thing with computing different string rewrites, or all kinds of different rewrites where there isn't just one answer, there are multiple different answers. So in this case, this is the initial combinator expression. These are different evaluation paths through that combinator expression. In the case of combinators, we're guaranteed if it terminates, it always terminates in the same thing. Okay, so these are different evaluation paths. These are different, each path through here can be thought of as a different evaluation strategy. Okay, so like leftmost, innermost, we're one of these and so on. This is a slightly expanded version of that picture that shows what we might call the updating events that happen. So this is showing in this particular branch, the updating of this thing to this happened, and that's what led to this result and so on. Now, one thing that is a powerful idea that comes from our physics project is the idea of causal graphs. This is just showing different evaluation strategies follow different paths through this multi-way graph. And these multi-way graphs can get considerably more complicated. So that's another multi-way graph for this. And let's keep going. This is a multi-way graph. These numbers are just showing the size of the combinator expression. And again, these are terminating results. They terminate. Different evaluation strategies will lead to different execution times here. And things can get quite complicated. You know, you get, there's a slightly more complicated one. This is a particular evaluation strategy leading down to this termination here. And let's see, here's another example. Let's see, we probably have some other examples here. This is still talking about, I think, the same one. Okay, this is an example of one that doesn't terminate. So these things that are still in orange here, those will just keep on going. They will here's a bigger version, I think, of the same thing. So this is a multi-way graph. This represents, so here, this is a single way evolution. Here, there was no choice about the updates that could happen. There was only one possible update that could occur. But here, we went distributed. We went our concurrent computation, so to speak. If we were thinking about these updates all happening in different places, all happening on different processors, let's say, this is a place where we started to be able to do things in parallel. And so then this multi-way graph maps out the set of possible different parallel evaluation orders that kind of occurred. So what we're seeing here in this particular case, there is a terminating case here where a bunch of paths lead to it. But in this case, there's also paths that do not terminate. So there is a particular, in the case of combinators, one can prove that a particular evaluation order, if termination is possible, will always lead to termination. But other evaluation orders will in general not lead to termination. They'll lead to things keeping on going. It's actually really good that multi-way systems can keep on going because that's how our universe works. And if it terminated like this, it would be the end of time, basically. This is sort of a discussion, a discussion of this question of evaluation order. And it's interesting to see in the case of combinators, we can this is just a whole study of evaluation orders. I don't know what kinds of examples I have here. Oh yeah, this is just the example. This is for a Fibonacci tree. You can say, well, what evaluation orders can you use here? And what you do, if you're evaluating the Fibonacci tree, one thing you might do is recurse all the way down to the leaves and then start collecting things up. That's sort of a depth first process. Or you can go to this level, 2 levels down, and you can say, okay, now let me collect together the F of 4s and evaluate those both together, for example. Let's see. Well, so combinators provide an example of where you can start talking about these evaluation orders. So let's let's maybe just I don't have too much longer here, but let's talk about how this relates to physics for a second, if people are interested in that. So what is the universe made of? What people have sort of assumed is that the universe, ultimately things in the universe are put in different places in space. You know, you think about Euclidean geometry, it's just you put a point at a certain position in space, but you don't talk about what space is made of. Space is just something that you put things into. Well, people might have said the same thing about, I don't know, something like water. Water is just a thing that flows, but we actually know water is made of things. It's made of molecules bouncing around. So one of the big sort of innovations in our theory of physics is the realization that space is made of something. And what's it made of? It's made of kind of these pure atoms of space. They're just pure abstract elements. And in fact, bizarrely, they can be thought of, okay, so what is the data structure of the universe? The data structure of the universe is just these pure abstract elements. And the only thing we know about these abstract elements is how they're related to each other. So for example, let me try and pull something up here. Let's say we, let's see, is this, okay, so we might just say, this is a piece of the universe, one and two are just sort of elements that will ultimately be atoms of space, and those are their relations. We can represent their relations in terms of a graph. In general, when we have relations that are like this, for example, with ternary relations, we can represent those in terms of a hypergraph. So in what we think of is, okay, the raw material of the universe consists of just a bunch of points, just a bunch of atoms of space. The only thing we know about those atoms of space is how they're related to each other. So in a sense, the ultimate data structure of the universe is just a hypergraph. Okay, so now what can we say about that hypergraph? Well, we can say, well, what about if this hypergraph is updated? What about if it has updating rules, a little bit like combinator rules, where we say every time, and I'm writing this not in Wolfram language notation, but would have blanks here after the X here. If we say, what is every time we see X blank, Y blank, X blank, the same X, Z blank, we transform it like this. So represented in terms of graphs, that's the transformation we're making. Okay, so a little bit like that cellular automaton I showed you, let's say we start from this graph here and we just run that rule. We run that rule with some particular evaluation order. Okay, so that rule will start building up things like this. Okay, we keep running it, we keep running it. Let's say we keep running it until we have 10 to the 400 nodes. What is that thing? What is that thing like? Well, what's interesting is there are all kinds of things you can get, but sometimes you can get things which have a very recognizable structure. Like here's an example of building up a structure which eventually, and well, here's a better example actually. This builds up a structure which eventually, when you just render the graph, and the only thing we have information about here is the connectivity of these nodes. So these are kind of atoms of space where the only thing they know is who their friends are. They don't know anything about their position. They just know the connectivity information. So in this case, what we build up is essentially something which in the large scale limit behaves like a two-dimensional manifold with curvature. And so this is what's happening is from this very low level sort of rewrite rule, we're basically building up this giant hypergraph. That giant hypergraph is a data structure. That data structure is space in our universe. And so you can ask things like, what's the dimension of that thing? Well, you can start, measuring little sort of geodesic balls in this graph, and you can estimate dimension from that and so on. You can estimate curvature, those kinds of things. You can start asking, okay, well, if that's what the universe is made of, what's an electron, for example? And what you start realizing is those particles are essentially topological obstructions in this hypergraph. It's a little bit like the cellular automaton, that rule 110 cellular automaton I was showing you, where it has these little particle-like things that are bouncing, that are moving around. So similarly, we haven't actually identified what's necessary for actual electrons and photons and so on. We only know the general theory of how this should work, that these things correspond to essentially topological, sort of topologically unremovable objects in this structure of this hypergraph. And most of the structure of the universe is sort of the maintenance of space, and all these little update rules and so on that are being applied, they're kind of knitting together different pieces of space. And and probably about 10 to the 1 minus 120 of the activity of the universe is involved with everything we know about the universe, all the electrons and photons and so on. And the vast majority of the activity of the universe has to do with knitting together the structure of space. So, okay, so then we can ask about things like, well, if that's what space is, what's time? Time is sort of the inexorable evolution of this hypergraph. And we can kind of represent, there's a kind of a complicated story here, because what's important in the end, this is going to get us into a different area, but if you're interested in how relativity and things like that come out of this model, what happens is an observer embedded within this evolving hypergraph is sensitive ultimately only to the causal relationships between the updating events. That produces this causal graph of causal relationships when to an observer, they are trying to say, let's see if I can find an example of this. This might be a good example. Okay, so this is a very simple case. This is not a hypergraph, this is just a string, and the rewrite rule is just a sorting rule. It says BA goes to AB, okay? And every event is represented by a yellow box here. And so in this particular case, sorting is confluent. It's what we call causal invariant. It doesn't matter in which order these events occur. Eventually, you'll just get sorted strings. But now we can draw a causal graph that represents the causal dependence of these functions, of these updates. Each one of these we can think of as a function. It has two inputs, two outputs. We ask of the next application of the function, does it have the inputs it needs to run? Okay, so we can represent that by a causal graph that shows what function depends on what previous functions, okay? So now we can say, well, let's choose a different evaluation order effectively. We then change the causal graph. We change where these boxes are, but the critical fact is that because of this property of causal invariance that this particular rewrite system has, the graph is always isomorphic. We don't change the structure of the graph. The causal graph is always the same. Okay, so it turns out that fact is what leads to special relativity in physics. And so as an example of that, we can kind of imagine a very simple graph. Let's see if I can pull this up. There's a very simple example of a causal graph. Now we say, okay, we've got the simple causal graph. We've got all these events happening. This is spacecraft takes off from the Earth. This is spacecraft lands on Mars. We have to ask the question, what counts as simultaneous events? And we can foliate this causal graph in a variety of different ways. We can say, we will consider it to be now on Mars at this time on Earth, so to speak, and so on. And so we're basically creating, these are our surfaces these are our space-like hypersurfaces in physics sense. These are our moments of simultaneity. These are our synchronization points in distributed computing. These set of events will happen at the same time, so to speak. Okay, but now we can imagine that, for example, we're moving across the system. And so we might conveniently choose a different foliation of the system. Let's say we're moving like that. We can say, let's reconstruct this system, making our foliations be okay. So there's sort of the foliations we will get when we're moving across the system. Now let's rearrange things so that we imagine that time is just, we're just standing still, and we are moving relative to, we're standing still and things are moving relative to us in some sense. And then it's like, well, what does the causal graph look like? And this is now the deformed version of the causal graph. This causal graph defines a partially ordered set, and the foliation is one that preserves the partial ordering of the partially ordered set. And so the thing that then happens is, if you notice this picture with its deformation, this picture is the transformation that we made is exactly a Lorentz transformation, and this the sort of the transformation of time is exactly what you expect from time dilation and relativity. And so in some sense, what you could say is that so let's imagine you're doing this computation, and let's imagine that you are using your computation to do as many updates as possible at a particular moment in this kind of reference frame. And then you say, well, I'm going to pick a different reference frame, and I'm going to basically use some of my computation to move in the reference frame and only some of it to do the computation, to do the actual updating. Then in a sense, it takes longer for the final result to be gotten. And so this is basically relativistic time dilation, in this case shown in a string rewriting system. And it's the same phenomenon. It's so you see kind of the phenomenon of time dilation happens in this kind of distributed computation setting when you have a notion of kind of a space-like arrangement of let's say processors. Okay, so just to give a little bit more of an idea of this, just as, so in these hypergraphs, there's a possible updating sequence, there's a possible evaluation order. In general, there are many possible evaluation orders that you can take. So there are many possible histories essentially for the universe. If this data structure represents space in the universe, there are many possible histories that can be followed in the evolution of the universe. And this is representing those. So there's some branching, sometimes there's merging, and it keeps going. Okay, so this multi-way graph represents the possible evaluation histories of the universe. Okay, what does this correspond to? Well, in classical physics, we imagine that sort of definite things happen. We throw a ball, it follows a definite trajectory. But in quantum mechanics, the key thing is that actually many possible things can happen, and we only get to measure sort of probabilities of what goes on. Well, it turns out in our models of physics, quantum mechanics is inevitable, and is a consequence of the fact that what you actually get from updating these hypergraphs is a multi-way system. And so what we see here is this multi-way graph being followed, and it turns out that well, it's sort of a long story. Maybe I shouldn't. People interested, I could say a little bit more about it. But basically, just as there is a notion of reference frames in relativity, there's a notion of reference frames in this sort of, well, okay, so each of these nodes in this multi-way graph is kind of a state of the universe. It's also a quantum state. And so what's happening here is that what we're getting is sort of a map of all these possible quantum states. And so, for instance, if we say, what are the quantum states that exist at a particular time, we can form what we call a branchial graph, which represents the common ancestry of states. And so here we're sort of mapping out what of these possible histories of the universe, which one is most closely related to which other one. And so this is a kind of space that isn't ordinary physical space. It's what we call branchial space. It's a space of quantum states, and it represents the this sort of represents nearness in the space of quantum states. And it turns out, I mean, long story short, the in physical space, the most sort of prominent feature of physical space is the fact that the presence of energy momentum or mass produces curvature in physical space. Energy momentum in our models is basically the density of activity in the network. And then, so what happens is there's a density of activity in the network, and that produces curvature in the network. And then shortest paths, geodesics in the network, which are the paths that particles follow, those shortest paths are effectively deflected by the energy momentum that produces the curvature that makes the geodesic be curved. So in physical space, gravity is a consequence, and we can derive the Einstein equations for gravity, much as one can derive kind of the equations of fluid mechanics from microscopic molecular dynamics. So here we're deriving the continuum equations for space-time from this microscopic structure of atoms of space and their interactions and so on. So anyway, we can do that in physical space. You get general relativity. In branchial space, you have the same kind of structure of deflection of geodesics by the presence of energy momentum, but instead of the corresponding derivation for motion in branchial space being something about gravity, it turns out that that's quantum mechanics. And the key result of quantum mechanics, the Feynman path integral, which kind of defines quantum mechanics, is actually the same thing as the Einstein equations. What the Einstein equations are in physical space, the Feynman path integral is in branchial space. So you might say, sort of, so what? What consequence does that have? Well, the whole point is that this whole multi-way graph thing, this is a map of a distributed computation. And all these different events happening at different places in space-time, they are like different events happening on different processes in a distributed computation. So for example, in physics, we have things like event horizons, the things that happen at the, around a black hole, for instance. Those event horizons are parts of this network that can't communicate with other parts of the network. There are, in distributed databases, there's this idea of eventual consistency. Eventual consistency is essentially our causal invariance property. It's what leads to essentially a relativity for those kinds of systems. It means that you can sort of program in different reference frames. You can think about the progression of the system with respect to different coordinate systems, and you'll always get the same result. But what's, I think, interesting here, and what's kind of, for me, the next big frontier, as far as I'm concerned, in sort of programming language development for us, is understanding distributed computation in terms of multi-way graphs, and understanding this process of things where there are many possible results and different kinds of things happen. And that turns out to be the story of quantum mechanics, and it turns out also to be the story of distributed computing. And what we get to do now is to import the things we know from quantum mechanics and quantum field theory and physics and so on into our thinking about distributed computing. Also, it's a two-way street, because we also get to export from distributed computing things to physics. And that's a whole other story about how that works. And in fact, one of the things that's been sort of exciting in the last few months is using our models directly to do, and using sort of computational ideas there to actually simulate black hole mergers and other kinds of things like this. But anyway, so that was not really what I had planned to talk about at all, but perhaps that was fun for people. And I think if we maybe have just a couple of minutes, I think perhaps the thing that if there's a what is the takeaway? I don't know. Our language has sort of been built to be as principle-based as possible. And when you are trying to understand how things really work in computation, that's a very important attribute. And so, for example, the things we've been able to do, the physics project has been purely the result. I mean, if I look at what caused this physics project to be possible, it was basically the trajectory of my development of SMP, which led me to understand a bunch of computational ideas, which led me to study these kind of what do simple programs do, which led me to things like principle of computational equivalence, which led me to other kinds of things, which led to things like creating kind of ways of representing things like graphs in our symbolic language, which led to more thinking about those kinds of things, which eventually led us to understand more about sort of what the underlying machine code of physics might be. And to my surprise, that kind of machine code of physics idea has now fed back into actual very practical things about computation. So if there are a few quick questions or comments, either on our live stream or in quotes person here, I'd be happy to try and address them. Otherwise, I better move along to my next thing, which I think, unless I've already run out of time here, let me just see. No, I have. Yes. Okay. We can a few more minutes if people are interested. Anybody want to ask anything, make comments, or should we? For another time, we'll talk about how these kinds of ideas about physics and distributed computing are relevant to blockchains. That's another different question.
Truly so. I just wanted to say that I got a very appealing response to my question that you, by the way, called silly. Unfortunately, I get all that kind of silly question all the time. That why did you want to invent your own language? And I think that the response that I got was that because I wanted to be, loose and fluid in every possible way that I explore the world, and I didn't want it to be tied up to a particular, structure that somebody else has thought of already. And
well, it's not quite. I mean, the point is that the goal of what I have been trying to do for the last 40 years is different from the goal of, I believe, and I have tried to get to know the creators of many of our programming languages, so to speak. I believe it's just a different aspiration from what people who build programming languages think they want to do. And, as far as I'm concerned, this is about letting computation, being able to represent everything computationally, which is a bit different from saying I want a language that I can use to get the computer to do the specific things that I want the computer to do. So it's kind of the aspiration has been rather different. And also, honestly, I think I was lucky that the ultimate structure that I started off using was this idea of symbolic expressions and transformation rules on symbolic expressions, because that's an incredibly powerful paradigm, which, we see. I don't really know. I'm not. I used to know sort of all languages back when I was first developing Wolfram language, but I've probably lost track now. But this idea of representing things symbolically, there's sort of shades of that in things like Haskell and so on. Which, by the way, from what I know of it, is a very elegant language, and people sometimes say, oh, that's like a such and such in Haskell. I think it's much easier to understand in our language because we've kind of given people more of a crutch of kind of all this kind of built-in structure in the language, which means when you come to a difficult idea, and there are difficult ideas, there's kind of more that you get to sort of scaffold that difficult idea on. And I think let's see. So, I mean, I think that the answer, for us, the answer is because we want to do something different than people who built other languages. I mean, I think that it's, as it's turned out, the kind of tower we've built is at this point rather tall. And, this is kind of the unique such tower because nobody else has been sort of crazy enough to try and do something like this. And it's a lot of work. I mean, it just checked off the last 40 years of my life, so to speak, doing this. And many other people, many other very talented people working on it as well. Let's see. There's a comment from AE about quantum computation. Actually, we are about to release our quantum framework for Wolfram language, which we sort of developed for many years. But what's made us release it now is that it can be compiled into multi-way systems. And so one thing you'll see, actually, there's a paper about this. I could probably point you to, if you look on our physics project website, you'll find this paper. There's a paper where we're taking quantum circuits and we're compiling them into multi-way systems. And then we're running theorem proving in the multi-way system representation, and then using them to generate optimized quantum circuits. So why is that exciting? Well, it's exciting because it's the best way of optimizing quantum circuits right now. But the other reason, as far as I'm concerned, that it's exciting is because if you want to know whether our theory of physics is right, it's pretty interesting if you can take the existing representation of quantum circuits and simply compile it into our model. So we're simply compiling the high-level quantum circuit description into our multi-way system machine code, and then that is sort of a proof by compilation that yes, it really works the same way as the quantum circuits. And I think that's I'll probably pull up for a second here. Let's see if I can pull this up. Just for fun. That's kind of a visual summary of our physics project that people might find of interest, of showing kind of this rewrite rule, the hypergraph, the causal graph. This is the whole multi-way causal graph. That's branch yield space. And it's kind of how the different features of our physics project fit together. But let me see if I can go back to, oh boy, how do I go back to the homepage? Just like this. Let's see if I can pull up latest bulletin. Homotop is in, wow, I haven't looked at that paper yet. Okay. Fast automated reasoning over string diagrams using multi-way causal structure. Then of a different direction, why does our universe exist? But let's see, here we go. This is about diagrammatic reasoning with an application to circuit simplification. So this is using the ZX calculus, which is a category theory-based representation of quantum mechanics, and probably somewhere here. I mean, I don't know. I didn't write this paper, so I'm not as able to. Okay, there are some pictures of mine which are being used here. That's always a good sign as far as I'm concerned. But this is someplace here. It probably is showing how you can go from. Okay, this is showing automated theorem proving in multi-way space. And somewhere here, it's probably going to show what actually happens in a quantum circuit. Is it? Is it going to show the quantum circuit? These are just results for time complexity of quantum circuits with different methods. So I'm not sure we're going to actually see a nice quantum circuit. I guess this is the quantum teleportation protocol compiled into multi-way systems, and then with essentially optimization done at the level of the multi-way systems using automated theorem proving. That's that. One of the things that I think is true is that I think the formalism of quantum computing is probably more interesting than right now than the actually running on a quantum computer, because although they have interesting physics, I'm not sure that they are yet at the point of being able to really do interesting computations. It's kind of ironic because I worked on quantum computers together with a physicist named Dick Feynman back in, when was it, 1981, 1983 type time frame. And we, or at least I could say I think Dick Feynman agreed with me about this. We never thought quantum computing was going to work. We always thought that while you would, how I would describe it today, you develop all these separate threads of computation that are sort of quantum parallel threads, but then you have to measure what actually happened. And as I would describe it today, you have to sort of knit together all those separate threads in the multi-way system to come up with a sort of definitive answer. And that process of knitting seems to take more effort than you gain in the parallelism. At least that's the sort of tentative conclusion that we have. But I think that the formalism of quantum mechanics and the formalism of these multi-way systems and so on is super interesting as a way of thinking about distributed computing and kind of a way of understanding a lot of processes, whether they're for computing or for chemistry or for whatever else, and very relevant if you're trying to merge those two together into molecular computing and so on. All right, I unfortunately have to go here. So I thank people very much, and I think we should wrap up. So thank you
very much, Stephen. It's been a great honor hearing from you today. You've been very generous with your time. Hussein, would you like to say a few words?
Yeah, I'm very thankful of everyone who participated in Primo today, and including Stephen. It was great insight for me as a programming languages person. Thank you very much indeed for accepting our invitation.
Thanks. Okay. Bye for now.
Thank you.